We've already seen some examples of systems of equations. We saw this example earlier. This is a system with two equations and two unknowns, namely x and y. Some other examples include this system here. This is an example of a system with three equations. And now we can see that there are three unknowns. Those are x, y, and z in this example. And here's an example of a system with also three equations, but this time we have four unknowns, x1, x2, x3, and x4. In all of these examples, we can search for solutions to these systems. We are looking for, as we saw earlier, a set of values for all of our variables, whether that's just x and y, x, y, and z, or x1, x2, x3, x4, or whatever we have, that we can plug into each of the equations that solves them all simultaneously. To get a little bit more formal with this, we say that a linear equation in the unknowns x1, x2 through xn is an equation that may be written a1 x1 plus a2 x2 plus dot 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 plus an xn equals b, where a1, a2 through an are real numbers known as coefficients, and b is also a real number. Notice that we've got a bunch of variables. Here we're calling them x1 through xn, but those can be called x, y, z, or whatever we want, depending on the problem. And we've got, possibly multiplying them by coefficients, adding them together, and then setting them equal to some other constant real number b. We're not multiplying any of our variables together. We're not raising them to any powers, right? We don't see any squared terms. We're not taking square roots. We're not applying trig functions or logarithms or exponential functions, right? So the main object we're studying in this class are these linear equations. Fairly simple when it comes to equations, but the complications come in when we ultimately view these in terms of systems of equations, systems of linear equations, and add in all these different variables. We say that x1, x2 through xn are called the variables in the equation. So we might call them unknowns or variables. And then by a system of linear equations or a linear system, we mean a set of linear equations written in a common set of unknowns. So we saw examples of that earlier. Moving to talking about solutions to formally define this idea of a solution to a linear system, that's going to be a set of numbers, x1 equals s1, x2 equals s2 through xn equals sn, that satisfy all the equations in the system. We call the set of all solutions the solution space of the linear system. So for example, we had this example earlier, x plus y equals 3, 2x minus y equals 0. We saw the solution to this was x equals 1, y equals 2, because it satisfies both equations. And we saw graphically as well as algebraically that this was the only solution to this. So this solution makes up the entire solution space for the system. One thing we looked at in an earlier video was this idea that our solution space might only contain one single solution. It might contain no solutions, so technically would be the empty set for that solution space, or it could contain infinitely many solutions. As we progress in the course, we're going to see different ways of sort of describing that solution space. In particular, when it is an infinite set, we want to kind of be able to break it down a little bit further and maybe understand these infinitely many solutions.